free to stop me and ask questions. Okay. Okay. So let me get started. So I'm going to talk about probabilistic programming. So this is a exciting new and emerging area which lies in the intersection of programming languages and machine learning. So in this talk, I'll show you a bunch of techniques which will hopefully convince you that techniques from programming languages are very applicable and useful in probabilistic modeling and machine learning. So has there been has there been a session on programming languages already, or have you guys gone through a course, lecture? Great. So all of you attended data flow analysis. So in fact, in a part of this talk, I'll also show you how data flow analysis can also be used to solve probabilistic models. Okay. So this is sort of joint work with a number of collaborators from Microsoft Research. So the blue clouds are interns and students who work with us, and the light clouds are other collaborators. So here's an outline of my talk. I'll start with a sort of very gentle introduction to probabilistic programs, and then I'll describe a programming language for probabilistic models, and then show you how these models can be solved using program analysis techniques. So like, for example, data flow analysis, which you saw earlier in this school. And in particular, there are three analyses which I'll describe. We don't have to sort of get into the details of this as yet, but all of them are based on program analysis. And then finally I'll conclude. Right. So let's start quickly with an example. So here is a application. It's called TrueSkill. So it's the skill rating system in Xbox Live. So hopefully many of you know what Xbox is, and there's a skill rating system in Xbox which tries to sort of match players with similar skills. So as you play Xbox, your skills are getting updated based on how you perform in various games. And the interesting question here is how are the skills modeled? And it turns out that probabilistic model is actually employed to sort of model these skills. Right. So here's a simple probabilistic model. Essentially what this is saying is that you have a notion of a skill. You have two players. This is a very simple model for two players, A and B. So they have skills, skill A and skill B. And essentially what this model is saying is that there is a certain prior on what the skill of A and skill of B is. So you have a certain belief. So for example, if it's Vishwanathan Anand playing chess, you have a certain belief with respect to what his skill is, and if it's me playing, you have of course a definite skill estimate of how I play chess. So these are the priors. So in the previous lecture, hopefully the notion of a prior distribution and so on was covered, right? So this is like your prior beliefs. They come from some Gaussian distribution. And then you have these performance variables which are noisy measurements of the skills. So as you can see, what's happening here is that performance of the player A is a noisy measurement or a Gaussian with mean skill and some variance, and likewise the performance of the player B is another Gaussian with skill B. Right. So essentially this is saying that the performance of player is not quite equal to the skill, but it's related to the skill. And the reason you want to do this is, for example, you and I can play a game, and perhaps even though you are better than me, you lost because you had a headache or didn't sleep well and so on. So it basically accounts for certain noise which is required for a probabilistic model. And then what this model is saying is that there's an event E, which is that the performance of A is greater than the performance of B. So you sort of sample the values of performances A and B from these Gaussians centered around the skills, and then you sort of get this event which is, or you define this event which says that A is greater than B, which sort of models the fact that A wins. And then the question you want to ask is, well, conditioned on the fact that you observed this event, what can you say about the skills of A and B? So we want to basically estimate these conditional probabilities, right? So conditional probability is also discussed in the last lecture. So this is exactly how TrueSkill works, in fact, in reality. So basically you have these priors, and then you have a model, which is this part, and then you have observations with respect to how players fare in various games. And then you want to update the skills based on your observations. Right? So this is an example of a probabilistic model, and it turns out that there are various applications of these kinds of models all over the place. So for example, in biology, life sciences, analysis of data, and even verification of programs. So the question is, one question is, once I give you this model, how do you sort of estimate these conditional distributions? right? And there are again a number of techniques to solve these kinds of models. The first is symbolic methods, like writing formulas using Bayes rule, and then sort of using exact and approximate methods. And the other is sampling. So essentially what you do is you sort of have this probabilistic model with parameters. In the earlier example, the parameters of the distribution were the skills, and you want to estimate these parameters by sort of repeatedly sampling from these distributions and then averaging over those samples, right? So there are two ways to sort of compute or estimate these conditional distributions. Is this clear? So what does this talk about? What is all this probabilistic programming and so on, right? So here's a quote which I like from this person, Kathleen Fisher, who runs the DARPA project for probabilistic programs. So DARPA is the US Defense Agency, and they basically have been running this project for the last couple of years. And the objective of that project is basically the following. So what they want to do is to do for machine learning what high-level programming languages 50 years ago did for software development community as a whole. So there's been a lot of advances in programming languages. So writing a piece of software is sort of almost a no-brainer given these high-level languages. So for example, if you program in C, Sharp or Java, you don't have to worry about things like how to allocate memory, how to free memory and so on. So you have these high-level languages. And then there are other high-level languages which also allow you to sort of look upon object-oriented systems as databases like LINQ, and functional programming languages like F#, OCaml and so on, which basically sort of increase the ability for a person to program quickly. And the hope is that with this DARPA project is to also enable people to sort of code up machine learning applications quickly. So that's why you need a programming language. So you want to basically give people the power to code up machine learning applications quickly without necessarily having the ability to understand what the machine learning is. So essentially what are these probabilistic programs, right? So probabilistic programs are just another way to specify probability distributions. So you would have seen in the earlier lectures that, well, one way to specify a probability distribution is a Bayesian network. Likewise, you can also specify a probability distribution by way of a probabilistic program. So what are these? So these are like usual programs written in regular languages such as C, C#, Java, Lisp or Scheme with two added constructs. So the first is a probabilistic assignment statement which gives us the ability to sample from a distribution, and the second is an observe statement which gives us the ability to condition values of variables through observations, right? And I'll say what these are through a number of examples. And like I said, the goal of a probabilistic program is to compactly specify a probability distribution, right? So you basically want a language by means of which you can specify a probability distribution, right? So what are examples of probabilistic programs? So here's a simple example. So here I have a probabilistic program which is defined over two Boolean variables C1 and C2. Essentially what I do over here is I have a probabilistic assignment which samples a value from a fair coin, which is a Bernoulli distribution with mean 0.5. The probability of heads equals probability of tails equals 0.5. I draw a sample from this and assign it to this Boolean C1, true being heads and false being tails. And then I toss another coin independently and assign its value to C2. And then I return this tuple C1, C2. So the question is, what does this probabilistic model or probabilistic program even mean, right? So in our world, what this means is that the meaning of this probabilistic program is the meaning of the probability distribution over its return expression. So in this case, I want to understand or know what the joint distribution over C1, C2 is. So in effect, right, what this program is saying is that it's specifying this table over here. Right. So it's basically saying that the joint distribution over these independent coin tosses C1, C2 is nothing but this uniform distribution, right? So that's the meaning of the probabilistic program. Let's look at a slight variant to this program, because I said there were two constructs, right? You've seen an example where you have probabilistic assignments. So here's the same example, except that I have this additional statement called observe C1 or C2. So what this observe statement is doing is that it blocks all runs of the program intuitively which do not satisfy the predicate in its argument. So this program is going to say a run or samples drawn from these Bernoulli distributions, if they don't satisfy this predicate C1 or C2, which roughly corresponds to the fact that you observe at least one heads, because you need at least one true to satisfy this predicate. and then you return again this joint distribution. So essentially the question, the meaning of this program is again the joint distribution over C1, C2, conditioned on the fact that you observed at least one hits. So it's like an implicit way to specify a conditional distribution, right? So if you look at the table again for this, well, this program likes all these runs, but doesn't like this run, C1 equals false, C2 equals false, because that does not satisfy this predicate, C1 or C2, right? So essentially what this means as far as this program is concerned is that the run which corresponds to C1 equals false, C2 equals false gets a probability of 0, and then you get a sub-distribution. If I just look at the earlier table where you get 1/4, 1/4, 1/4, and then upon renormalizing to make it a probability distribution, you get 1/3, 1/3, 1/3. So the meaning of this program is this distribution, which is again uniform but defined over this subspace over here, right? So essentially this observe is used to basically condition values of distributions in various ways. So here's another interesting example. So here's a probabilistic program with a loop, and essentially again it's doing the same old coin tosses, and it keeps sampling them until it satisfies this predicate, and that's encoded with this while loop over here. So this is going to keep sampling C1 and C2 until the predicate C1 or C2 is satisfied, right? So so have you seen this program before, or does this look familiar? So what's the connection between this program and this program? Seems like they're the same, right? So because this guy is basically saying I block all runs of the program which don't satisfy this observe statement, and this chap is saying, well, keep tossing coins until you satisfy this. So the result looks the same, and indeed this program is equivalent to this program intuitively. I have not formally proved it, and of course since they're equivalent, the meaning of this program is the same as what you saw earlier. Just so turns out that it's harder to directly sort of get this table from this program or infer this table from this program because it's not as obvious as this one, but you get the idea. So here's another, yes? Oh, a very great question. So essentially, right, I will formally define, so right now I'm informally defining what the meaning of the probabilistic program is, but when I say you can sort of sample, and one way to do inference is to run these programs and do statistics over the samples, I'm just looking at terminating runs. I'm ignoring all non-terminating runs. So essentially the fact that this while loop can be encoded as an observe here basically means that you're only sort of encoding terminating runs. So here's another example. Here what I'm doing is, well, I assign B to true, sample a value of C, and then while C is true, flip B and keep doing this until C is false and then return B, right? So have some of you, given that you've seen probabilistic models before, and of course what am I interested in? I'm interested in the distribution over the return expression, which is B. So the question is, what is the probability that B equals true? What is the probability that B equals false? Right? So anyone knows the answer to this? Have you seen this distribution? It's like, or in other words, okay, what's the connection between, okay, maybe let me not ask, have you seen this before, right? What's the connection between B equals true and the number of iterations of the while loop? Yeah, so you're a computer science person, right? Say what that means. You're saying it in English, right? So you're right. I mean, so essentially, the probability of B equals true is exactly equal to the probability of executing this loop an even number of times, right? So, and just like you said, you just compute this geometric series, half, 1/8, 1/16, and so on, and you get 2/3. So therefore, the meaning of this program is this table over here. Clear? And as a final example, let's look at a probabilistic program for the model that we saw earlier, true skill, Xbox Live 1. Right? So here I just have a code snippet for 3 players. So I have 3 skills, skill A, skill B, skill C, and I have 3 games. First game A and B, it's A versus B and A wins, so therefore you have performance of A, which is a noisy measurement of skill, performance of B, which is a noisy measurement of skill B, and since A wins, you observe performance of A is greater than performance of B. Likewise over here, B versus C, B wins, you observe performance of B is greater than performance of C, and finally A wins, A plays C and A wins, and you observe that performance of A is greater than performance of C, and you want to return skill A, skill B and skill C. And I've sort of used this bracketed notion here just to say that I'm not interested in the tuple here, I'm interested in the individual probabilities of over skill A, skill B and skill C, okay, not the joint. So the question that is being asked here is, well, can you tell me what the new values so when you started the program you believed that the skills were these distributions, then you played all these games, and then you want to ask the question, conditioned on all these observations which correspond to the games being played, what can you say about the new skills, right? So this is exactly the true skill. So I've written it, the true skill model, and I've written it as a probabilistic program, right? So before so what I've shown you so far is a way to specify conditional probability distribution using a programming language, and what you'd also seen is that hopefully is that the program basically specifies distributions like this, and these distributions are all implicit. It's not obvious by looking at this program that this program's distribution is this, right? So I'll say what this exactly means a little later, but before I say what that is, let me also connect probabilistic programs to probabilistic models that you are familiar with, the kinds of models you would have seen from the last lecture, right? So let's look at Bayesian networks. So did you look at Bayesian networks in the last lecture on probabilistic models, right? So let me just quickly recap, because it's been a very long time since you saw what a Bayesian network was. So it's a DAG in which every node is a conditional probability distribution, right? So let me just explain that quickly with an example. So here I have a Bayesian network from this very nice book called Probabilistic Graphical Models by Daphne Koller and Friedman, and this is a very simple model which basically was this the same example used in the earlier thing? Brilliant. So you know what this is, right? So I don't have to get into details, right? So essentially the meaning of this Bayesian network is essentially this joint distribution, right, which is the pointwise product of all these tables, right? That's the meaning of this network, and given this network you can ask various questions like the one shown over there, right? But what's the connection between this and probabilistic program? So it turns out that, if you look at this Bayesian network, you can also write a program which corresponds to this network. So essentially what this is saying is that, well, I have a difficulty which has a certain prior distribution, and you know that the prior distribution is this one here, 0.6, 0.4. So you say basically D is sampled from a discrete distribution with these parameters, then intelligence I gets its value from this discrete distribution, and then this snippet basically encodes the conditioning, right? It's basically saying if I equals 0 and D equals 0, then G gets a certain value. That's basically sort of directly encoding the conditional probability table for grade, and you know that that's basically parameterized by difficulty and intelligence. That's what this snippet is saying. And likewise the SAT score is dependent on the intelligence of the student, and therefore you have this if statement which encodes that conditioning. And the fact that the student gets a good grade or not in a course, gets a good letter or not, depends on his grade in the course, and that's modeled by this if statement over here. So you can just take any Bayesian network and write up a probabilistic program here, right? Another example is Markov chain. Was this also covered in the last lecture? Markov chains? No. So these are just like, most of you have done a course in automata theory and so on, right? So these are like finite transition systems, with the difference that you have transitions with probabilities on them. So for example, I have the state S1 which can go to either S2 or S3, and the transition from S1 to S2 happens with a probability 0.01, and the transition from S1 to S3 happens with a probability 0.98. Right? It's a probability distribution over transition, so therefore these must add up to 1, and that's sort of encoded by this matrix over here, right, which basically tells you the transitions of going from 0 to 0, 0 to 1 and so on, right? This is a transition matrix. It's like a graph, like a incidence matrix of a graph, except that you have these probability values. And the sum of all the rows of if you take each row and the sum of all its entries basically must be equal to 1 because it's a stochastic matrix. And you can ask various questions. So for example, if you have an initial vector like a prior or something over these states, the probability of S0 is something, S1 is something, S2 something, S3 something, that can be represented by as a column vector. And if I wanted to know what's the probability of all the states given that you make one step in this Markov chain, you basically just multiply that with this matrix. Right? So what does the probability distribution of the states look like when I sort of traverse this Markov's chain in one step, two steps, three steps, and so on. And you keep doing that, right? Keep multiplying this matrix with the initial vector. You finally, under some conditions, you will see that the vector or the probability distribution over these states does not change, and that's called the stationary distribution of a Markov chain, right? And that stationary distribution is basically the meaning of this Markov chain. Just like I said that the distribution over the return expression of the program is the meaning of the probabilistic program, the meaning of this Markov chain is its stationary distribution, right? So what's the connection again, right? So here's a nice example due to Knuth and Yao, which is a technique which tries to simulate a dice with a fair coin. So you have a coin which has heads or tails, in this case 0 or 1, and both of them occur with equal probability. And the question is, what this Markov chain is basically saying is that you can actually use the dice to simulate, you can use a coin to simulate a fair dice where the probabilities of each of these states 11 through 16, which are shaded, represent valid results or outcomes of the dice, which happen with probability 1 over 6. And it turns out that even this can be represented as a probabilistic program. So essentially what this program is saying is that it's just sort of encoding this Markov chain directly. So if you look at the switch case, so basically you have a boolean which is a coin which you flip, and now you want to ask the question based on the current state which is set by this guy and the result of the coin, you basically ask the question what should be the next move. So for example, let's say your current state is 2 and you flip the coin, right? That corresponds to this guy over here, this case 2, and it says that if the coin returns a true, you go to state 5, otherwise you go to state 6, right? And if you look at this main function here which sets up the state, it basically says, well, keep doing this flipping business until you see a value of x which is greater than 11. Essentially what it's doing is keep sort of making these moves in this region until you see something which is between 11 and 16. And if you work out the math, it turns out that the probability of return x equals 11 through 16 is exactly 1 over 6. Right, so there's a connection between probabilistic programs and all these well-known models. Then the question you might ask is, why do I need these probabilistic programs? Why don't I work with my favorite probabilistic models? There are two reasons for this. One is it turns out that probabilistic programs are much more expressive than, for example, Bayesian networks or Markov chains in terms of the kinds of problems they can model. And the other thing is, it's also a natural way to sort of, a program is a natural way to sort of model a process or also write down an implementation. And it turns out that if you put in the effort to write up these specs, the hope is that people can build tools around these specs which will do the inference for you for free. So what do you mean by that? What do I mean by that, right? So essentially, what is this thing called inference? So you've seen that the probabilistic program implicitly specifies a probability distribution, which is given by the table that you saw earlier. And the goal of inference is to infer the implicit distribution implicitly specified by the probabilistic program. So in the next few slides, let me sort of tell you what this formally means, and then we'll get straight into this business of exploring techniques to perform inference. So given these probabilistic programs, right, there are lots of tools which can automatically compute those tables that you saw earlier. So I'm using the word table in a very loose manner, assuming that they're discrete distributions, but some kind of closed form representation for the probability distribution, right? So there are a number of tools which do this. So for example, there's this tool called Church from MIT, there's Info.net from Microsoft Research, there's another tool called R2 also from Microsoft Research which our group is building, and there's a tool called Blog from Berkeley. Bugs is a tool which was developed like 30 years ago for Bayesian networks. So this is a nice tool which actually takes Bayesian networks as input and then automatically synthesizes an implementation which does inference for you. So, and the nice thing about this is that you as a domain expert sort of focus on the modeling aspects and not really worry about inference or machine learning or whatever happens under the hood. Right? So there are a number of tools, and in the last couple of years there's been a lot of excitement also in this area, because DARPA which is the US defense and funding agency, proposed this project called Probabilistic Programming for Advanced Machine Learning, where they basically propose some grand challenge problems, like for example, can you design languages / tools which enable people to sort of program machine learning applications without really understanding the details of machine learning, and this has caused a lot of excitement and also lots of interesting problems and solutions. I wanted to say something else, but I've forgotten, so I won't say it. So, right. So, and the high-level goal is, in some sense, given that machine learning is such a hot area these days, the whole objective is to sort of democratize machine learning. Right. So that's why they proposed this project. Right. So, so the whole point of this talk is to sort of somehow, in a sense, convince you that if people are willing to write up probabilistic models as programs, perhaps techniques from programming languages, software engineering, compilers, data flow analysis, maybe could be used, perhaps be used to sort of solve these models. So the way the current state of the art is structured is as follows. Given a probabilistic program, which is your probabilistic model, these tools that you saw in the earlier slide will sort of define a compilation or a transformation from the probabilistic program to a well-known probabilistic model, like a graphical model, Bayesian networks, factor graphs, or whatever they are, and then use existing algorithms to solve these models. And our whole take with this area is that if people are willing to write up probabilistic programs, then powerful techniques from program analysis and programming languages can be used to solve this problem. And it also turns out that this translation, the program has lots of information in terms of not only the syntax but also semantics. If you do this conversion, right, there's no one-to-one mapping between the programs to Bayesian networks, and there's a lot of information that is lost in translation, which also makes the other techniques a little inefficient. So what I'll show you for the rest of the talk is two things: how to compute the distribution specified by the probabilistic program efficiently using program analysis, and also give you a sense for what it means to prove the correctness of these algorithms. So what is really lacking in the machine learning area is that people come up with a bunch of techniques or algorithms, but they don't really focus on correctness. So in the sense that there are a number of tools which do inference for probabilistic programs, but the answer that they compute, right, is it the same as the distribution specified by the probabilistic program? I mean, that hasn't been explored so far, and by using program analysis techniques, we're able to bridge formal methods in machine learning. Right. So for the rest of the talk, let me focus on simple imperative language for probabilistic programs. So this is like a regular programming language with types and so on and so forth, assignments, sequential composition, conditional, blah blah blah, and so on. But like I mentioned before, the only difference from a standard programming language is that you have this ability to sample from distributions and the ability to observe expressions. Right? That's the only two differences. Right? So I'm going to use this language, which is a simple thing. And once you define a programming language, has there been a lecture on program semantics and so on? No. So it doesn't matter if I don't finish the slides, but at the very least, I want to basically convey to you that it's important to sort of think about program correctness when you deal with all these things. And I'll also show you some techniques which you will learn later, maybe in programming languages courses, which will sort of maybe drive home the importance. So this is syntax, right? I mean, I just told you that this is the programming language. I really haven't told you what it actually means, right? And for that, you have to define a semantics. So basically, I've also, by way of examples, told you that the meaning of a probabilistic program is a probability distribution over its output states, the return expression. I need to formally define this. So And there's been a lot of work on defining formal semantics of probabilistic programs. So there's this beautiful paper by Dijkstra, which was written way back in 81, and also some recent papers by Andy, Gordon and gang. And we've written some papers as well, which formally characterize the meaning of probabilistic programs. What does it mean? I mean, this is a very loose statement, right? So I need to basically define a programming language and actually say that the meaning of the probabilistic program is indeed probability distribution, right? But in the next few slides, let me sort of give you a rough sense for how people define these kinds of things. So essentially what I'm going to do is define this operational semantics of a slightly restricted language, which is Boolean probabilistic program. So let me just assume that my domain is Boolean. I only have Boolean variables and I can only sample from Bernoulli distributions, right? So now what the meaning of the probabilistic program, what does it mean to define an operational semantics, right? Essentially what I need to say is that if I have a distribution and execute a statement, then I get a new distribution, and I keep, and in the course of executing this program, you are sort of changing the distribution, and by the time you come to the return expression, you get the distribution that you want. And I need to define how does the assignment statement modify this distribution, how does the conditional statement modify this distribution, and so on. But in order to do that, I need to be a little more precise. So I'm going to define the notion of a state, which is mapped from variables to values, right? So standard notion of a state. And gamma is the set of all states, and I have this configuration, which is this tuple, which is a state comma statement, right? And essentially, right, the operational semantics is quite simple. You're just going to define or look upon the program as a transition system, right? So essentially what I want to say is, well, suppose you are in a state sigma and executed the assignment statement x equals e, right? What is the resulting configuration? So the operational semantics basically says that the meaning of the probabilistic program is defined as a transition system over these configurations. And remember, the configuration is a tuple sigma, which is a state, and a statement. So if my statement is an assignment and I have an input state sigma, after executing this guy, I go to a new configuration, and this one here basically says that I go to that configuration with probability 1. There is no probability here, right? And essentially, what is that new configuration? Well, it's basically the earlier state sigma with the value of x updated to the value of e evaluated under the state sigma. Does it make sense? So let me say this again, right? So I'm in a state sigma and I execute an assignment statement, right? Essentially, you know that x is going to get updated, but it's going to get updated to a value which is equal to the value of e in this state sigma. So suppose, let's say e was y plus 2, right? Then essentially the value of x is sigma of y plus 2, right? It's the value of y in this state sigma plus 2. I just update that, and then there's nothing else to execute. So that's the meaning of this assignment statement, right? So let me do one more, right? So let's say the statement is a sample statement, which is x equals Bernoulli R. Essentially what this is saying is, well, after executing this statement, I get a new state where x is given a value true with a probability r, and x gets a value false with the probability 1 minus r. Is this clear? Right? So that's why the probability thing comes in. It only comes in for these Bernoulli statements, right? And then let's look at one more where I have x equals observe. If I start in a state sigma and execute the statement x equals observe e, then with probability 1 I go to the same state sigma if sigma of e equals true, right? And so on and so forth. So I probably won't go through all of this, but you get the idea, right? So essentially the operational semantics is given as this transition system, and then it gets more complicated for rules. So now, given this transition system, right, if I run the program, right, what do I get? So when I run the program, that's called omega, it basically starts with an initial configuration and then keeps running the program until there are no more statements to run. That's what the skip statement is saying. Skip is like an OOP, right? And the probability of this run, omega, is nothing but the product of all the probabilities that you encounter during this run, right? And to cut a long story short, basically, by sort of writing down these rules precisely, you can define the meaning of the probabilistic program as this expression here, which is basically saying that the meaning of this probabilistic program is nothing but the probability distribution over its output states, right? So I'm not sure whether you guys know what the lambda notation is, but if you don't, it doesn't matter. But the meaning of this is to say that given an input state, the output of the program is nothing but the probability of the return expression with respect to that input state, right? So one of the ideas we have is, one of the thoughts is to basically use program analysis techniques to compute this distribution, right? So basically again go back to that example where I have a table. So this is just a formal way of representing that table. So I want to compute this table, right? But I want to just use program analysis techniques. I want to look at the text of the program and then compute this table, right? So how do I do that? So let's go back to this example we had over here, and the idea is pretty simple. So I have the same program that you saw, which blocks all runs except for the it blocks the configuration C1 equals false, C2 equals false. So now let's see how I could do an analysis of the program. So essentially what I'm going to do is to sort of go through this program line by line and then see the effect of what the distribution looks like. So for example, if I were to execute the first statement, C1 equals Bernoulli 0.5, then I get this table, right? Well, after executing this table C1 equals Bernoulli 0.5, you know that the distribution at this point is exactly this one. C1 can get a value 0 with half and 1 with half. Clear? Now if I execute the next statement, actually yeah, so what do you think I'll get after? If I basically now give this state to this statement now, what is the table I'm going to get? What table am I going to get? Okay, I'm going to take this table and push it through this assignment statement C2 equals Bernoulli 0.5. And of course C2 equals Bernoulli 0.5 has nothing to do with C1. So what table am I going to get? All the 4 configurations, right? So I get this 1/4 thing. And then I'm going to take this table and push it through this observe statement, right? So how is this observe statement going to transform this table? It's going to knock out that row which corresponds to C1 equals false and C2 equals false. And then finally, since I'm returning C1, C2, I'm interested in returning a valid distribution, so which means that I need to normalize this table because this is just a sub distribution, and I get this answer which you saw earlier, which is this uniform distribution with parameter 1/3. And that's it. I mean, so what's the problem with this approach? I mean, it can't be so simple, right? There must be something more to it. So I've just written up these tables and I just pushed it through the program, and I've told you that this is how you compute conditional distributions, and that's it. That's the answer. Right? Seems like a very non-scalable way of doing things, right? Because the tables will grow exponentially with the number of variables, right? So again, I mean, the people in program verification community have figured this out, where you can use data structures to effectively compress predicates, and in this case we use a data structure called arithmetic decision diagram, which is nothing but a decision tree, and you guys know what a decision tree is, right? I've just taken a decision tree, and if you compress it into a DAG, you get arithmetic decision diagrams. So essentially what we do is to take those tables and represent them using this arithmetic decision diagrams, right? So for example, the first table, which was just the uniform distribution over C, is represented by this guy over here, right? And it basically says, well, regardless of what the value of C1 is, you get a value of half. This one is saying, well, regardless of what the values of C1 and C2 are, you get a value 1/4. And then, you know, you when you filter, you get this DAG over here, and the leaves basically represent, it basically tells you that if you go with the value of C1 equals 1 and C2 anything, it's 1/4, and so on and so forth, right? So it's just a representation. It is still exponential, right? But in practice, these things work very well. So that's one idea, right? And there are various, and we don't have to build these data structures ourselves. And there are packages, libraries, which basically allow you to use these data structures. So essentially, what we do in the implementation is to sort of take those tables and represent them using these ADDs, and it turns out that it works really well in practice. But that's not all, right? I mean, essentially, I need to sort of tell you now that I need to sort of formalize this process that I showed you by way of illustration over the statements of the program, right? I need to tell you how this transformation actually happens over each statement in the program. Oops. And each statement of the program is formally represented by the operational semantics that you saw earlier. So essentially what we have, and I won't go through the details, is an algorithm which will take an input distribution row over the states of the program and then compute an output distribution of the states of the program. And what the algorithm does, and that's what I'm trying to sort of show over here, is that for every case, if it's an assignment statement, well, this is the formal meaning of the distribution over that assignment statement. And if you sort of spend some time on this, this expression is sort of very related to the expression that you get when you actually execute the operational semantics of the program. Right? So this algorithm basically sort of does this for every statement, and then and then what we can show is that when this algorithm, when it terminates or computes its fixed point, because you have loops and so on, the value or the meaning or the result of the algorithm is exactly the same as the distribution specified by the operational semantics. That's very important to show, right? Because you can define some algorithm which computes a distribution A, and the meaning of the probabilistic program might be a distribution B, and that doesn't make sense. You need to show that A equals B. So the whole point of this work is to sort of connect the result of the algorithm to the operational semantics of the program. But of course, all is not well. I mean, of course, there are cases where the algorithm might not terminate. So here's an example. So I have a really simple program where you have x equals true, and I keep toggling x forever, and then return x, right? And it turns out that if you run the algorithm that you saw earlier, which I skimmed through, it basically keeps on toggling between these two distributions. It basically either thinks that the distribution over x is either a point mass over 1 or 0. So it keeps flipping. So there are problems. It doesn't always terminate, but it works reasonably well in practice. And then, you know, the algorithm that I described is over discrete distributions. And there are various tricks you can use to sort of get it to work over continuous distributions. So one trick is to sort of represent, approximate continuous distributions as discrete distributions by converting them to histograms. And then there are some others, and I'll skip them in the interest of time. Right. And so we built a tool based on this and over a number of reasonable benchmarks and compared it with existing belief propagation based algorithms. So I don't know if belief propagation was covered last time. So there are techniques which are well known which perform inference over Bayesian networks and so on. And we compared this algorithm over a probabilistic program with well-known algorithms over Bayesian networks, and this algorithm works really well, and that's the point of this thing. So that was just one example to show you how data flow analysis could be used to compute these distributions. So were any of you able to sort of connect what you saw here with the data flow analysis lecture that you saw earlier? I mean, do you see the correspondence, or it's too vague? Because even in data flow analysis, I don't know which problems, which examples did you look at, like reaching definitions or something, is it, or live variable analysis? So it turns out all of those analysis, right, basically syntactically go through each of the statements of the program and then compute the expression of interest by symbolically executing the program. So what has happened here is I've not run the program. It's like a compiler. I'm just looking at the static, I'm just looking at the program text to estimate what the results of the program might look like. Right, and essentially, and the nice thing about the approach is that, well, whatever you compute is finally tied back to the meaning of the probabilistic program, which is the distribution over its return expression. Okay, so let me switch gears slightly and go to another example. So I've shown you how data flow analysis can be used to compute these distributions. Let me also show you how other program analysis techniques can be used to build efficient inference algorithms. So another way to perform inference, like I showed you in one of the earlier slides, is to do sampling. So in this case, right, what you would do. So here's a very well-known example due to Judea Pearl, who won the Turing Award a couple of years ago. And essentially what this model is trying to say is that imagine you're at work and or maybe I'm giving this talk right now and my neighbor calls me and says that my burglar alarm has gone off. And I know for a fact that the alarm can go off either if there's an earthquake or if there's an actual burglary, and conditioned on a number of events. So this program is basically giving you priors over earthquake, burglary, and giving you lots of events which are conditioned on various other events. And the question that is being asked here is, conditioned on all these events, what can you actually say about the probability of a burglary? And the thing to note here is that I'm interested in the probability of a burglary only if my neighbor called me, otherwise I'm not interested. So therefore you observe a called called equals true basically means my neighbor called me. Called equals false is an irrelevant event. So which is the reason why, conditioned on this whole distribution specified by these if then else statements, I sort of give another additional condition which is called equals true, and based on this observation I want to ask the question, what's the probability of burglary? So one way to estimate the probability of this burglary is to run this program multiple times and then just compute the fraction of runs where burglary equals true. Sounds reasonable, right? So and that's sampling. I just run this program, and I've already told you that the meaning of a probabilistic program is the distribution over its return expression. So if I just run this program multiple times and compute the fraction of runs where burglary equals true, then I have an estimate, right? So that seems like a reasonable way of doing things, but there's a problem. So the problem is that it's not every day that my neighbor is going to call me. Only sometimes, right? I mean, burglaries don't happen unless you live in some areas, but generally speaking, you don't have burglaries every day. So the probability of my neighbor calling me is a low probability. So which means that every time I run the program, right, it's very likely that the observation is not going to be satisfied. I run the program, I get called equals false. Run the program again, called equals false. And this keeps happening, and I have more samples, and therefore I can't estimate the probability of burglary. So that's a recurring problem, and this is very analogous to the notion of rejection sampling. So essentially the rejection sampling is a well-known technique where, well, I have a distribution and I have some certain constraints, and I keep drawing values from the distribution, right? So let's say I have a distribution which is a Gaussian with mean 10 and variance 20, right? But I only want to draw, for example, positive values. Maybe x greater than 0 is a constraint I have. Essentially what I do, the one way to sort of get values which satisfy x greater than 0 is to draw a value from the Gaussian, then check whether it is positive. If it's positive, accept. If it's negative, reject. But if the probability of the constraint is very low, then it's very likely that most of the times when you draw a sample, it's going to get rejected. Right? So that's exactly the problem that is happening here. So what do you do? Right? So the whole question is, I have this probabilistic program, and I want to ensure that whenever I draw samples from my assignment statements, which happen somewhere at the top, then all the observations which happen somewhere in the bottom of the program, somehow I want to satisfy them, because I don't want to do this wasteful computation of running the program over and over again. Right. So it's a very simple idea. So the simple idea is to take these observations and sort of hoist them up all the way up to the sample statements. Right, and essentially what I'm roughly trying to say is take the observation, which is a condition, and compute the inverse of that observation with respect to every statement. And if I basically compute these inverses all the way up to the sample statements, then I know for a fact that these certain conditions must be satisfied right at the probabilistic assignment right at the point where the probabilistic assignments occur. So for in this case, what I want to do is, perhaps there's a way I can push this observe call all the way to each of these these sample statements. That way what I can do is, when I sample burglary, right, I know exactly what its value should be. Right? So I want to do that. I know exactly what its value should be so that this observe call is satisfied. Right? So for that, right, essentially what we do is take the program and transform this into this other program. So essentially what I've done is, I've taken this observe and pushed it. So for example, I'll ask questions like this. In order to satisfy the observe over here, which is that call must be equal to true, what should be satisfied before executing the statement called equals Mary wakes and phone working? Right? So basically, intuitively what I'm saying is, well, if I have to satisfy called here, I better satisfy Mary wakes and phone working at this point, because if I did and then I assign Mary wakes and phone working to call, then call is going to be true, right? So I keep doing this, and essentially that's what I'm getting, right? So essentially, in order to satisfy observe called here, I need to satisfy Mary wakes and phone working here, Mary wakes and phone working here, phone working here, phone working here, and so on, right? So essentially what's happened is that I've taken this called and pushed it in a backward manner in the way I just described informally. And the nice thing about this program is that I can sort of define a new sampling procedure which is sensitive to the fact that there's a condition right after the sample statement, and if I do that, then I'm guaranteed to satisfy the call. So what's the big deal with all of this, right? So essentially, right, this whole business of pushing things back in the program is very well known in programming languages and verification. So the process that I described earlier informally is called Dijkstra's weakest precondition. It's due to Dijkstra. So essentially, so he defined a bunch of rules which basically say that if I have a predicate phi, right, and I want to satisfy phi after the assignment statement x equals e. I think I have a picture here. Yeah. So let's say I want to satisfy x plus y greater than 5 after executing x equals 3. Right? The question being asked is what should be satisfied, what should be true or what should be valid before executing the statement x equals 3. Yes? Right, yeah, exactly, y greater than 2, right? So then how did I get that? Essentially what I did was I replaced the occurrence of x with, over here with 3, and then I get 3 plus y should be greater than 5, which is y greater than 2. That's exactly what this rule is saying. And then of course we have defined specific transformations for, so these are for regular programs which are deterministic / non-deterministic. One has to define this for non-deterministic programs, and I don't want to overburden you with that, but there's a way to do it. But here's the point, right? To basically just hoist these things in some way so that you get those statements. Right? So again, what this is saying is, you know, if you take a particular path in the program, you can start with true and push it backwards. So for example, what this is saying is, in order to satisfy observed call must be true at this point. Many wakes and phone working should be true at this point, and so on and so forth. So this is nice. So we basically have a way by means of which we can hoist the observed statements all the way up to the probabilistic assignment statements. So then what? Right? Then what you do next is explain in a couple of slides. But what is even more important is I need to show that by doing this transformation, right? I basically sort of took a program with an observed statement and then I hoisted up these observed statements and added additional observed statements. I need to show that this this transform program, right? In the earlier slide, you had a program to the left and you have a program to the right. Both of them are semantically equivalent. I need to show that the distribution represented by the program to the left is the same as the distribution represented by the program to the right. And that's described in a paper, and I won't get into the details of that. So, but let me tell you how the sampling happens, right? So I have this program again, which is the transform program, and you have to sort of a leap of faith here is that this program is the same as the original program that you started with. So here's what I'm going to do. Essentially what I'm going to do is to run this program, but whenever I come to a sample statement like this, phone working equals Bernoulli 0.6, I'm basically going to constrain this distribution according to this condition over here. So in this case, I will basically sample from this distribution, but I'll constrain the sample to be equal to true because I need phone working to be equal to true. So the general idea, so this is like a degenerate example because in this case it means that phone working equals true. But in the general case, essentially what you're going to do is to sample the distribution conditioned on the observation immediately following it. And if you do that, then what you can show is that the answer that you compute is exactly the answer that you desired, and this technique has no rejections because whenever you sample, you are doing this sample according to the condition immediately following it, right? And again, you need to show that this sampling procedure, which I sort of roughly defined, which I'm calling sample pre, produces the same answers as a rejection sampler, right? So I just wanted to quickly give you these an overview just to say that, you know, there are interesting problems and there are hard problems, and there are various interesting ways of solving it using PL techniques. So this sort of implementation of this algorithm is built in this probabilistic programming system called R2, which we're building here in Bangalore, and it's going to be, if you want an implementation I can hand it to you, but in some sense we're going to make a public release of this in a couple of weeks time, and maybe in a couple of months time make it open source as well. So how does this whole thing, right, basically compare with existing tools? So there's a tool called Church from MIT, and I won't get into details, but as you can see, yeah, we're much better than Church. So it's a very efficient algorithm, and unlike other techniques, it's based on program analysis techniques. So here's another example of how program analysis techniques is useful for performing inference. So as the last part, given that I have only 4 minutes left, let me do I have 4 minutes left? Yeah. So let me quickly give you another example, right? So another example of how techniques from programming program analysis will be useful. So in your previous sort of ramp up lectures, did people talk about slicing and so on, program slicing as a way to do debugging and so on? No. So here's another question, right? So I have a program, and the objective is to compute a smaller program. Why? You want to compute a smaller program because if you sort of feed the inference engine a smaller program, hopefully it will do better, right? So essentially the whole objective is to take a program and remove all statements in the program which are not really required for the purpose of inference, and I'll say what this is in the next slide, right? So you want to come up with a smaller program. So this is very standard for regular programs. It's not so standard for probabilistic programs. So the question we want to ask is, remove all statements in the probabilistic program which are not really required for its query or return expression, and in such a way so that the result is still the same, right? So let me take the example that you saw earlier in the earlier lecture, this whether a student gets a good letter, that example. This is the program here, and so here the objective is to sort of do the following. You want to basically remove all statements in this program which are not really required to compute the probability over S, which is whether the guy gets a good SAT score, right? So that's the objective, because if you could do that, then hopefully the tool like R2 will consume a smaller program and then be much more scalable. And the way standard program analysis techniques would work is to sort of build this dependence graph, which is not surprisingly looks very similar to the Bayesian network, but this is a dependence graph which is basically saying that, oh, the variable G depends on D and I, variable S depends on I, variable L depends on G. This does look like the Bayesian network, but I am calling this a program dependence graph, and this graph has been derived from this program. And this dependence could either be control or data dependence. So what do I mean by that? So if in this case everything is control dependent, because L depends on G because L is going to get different values depending on what the value of G is. So it's like an indirect dependence. So given this graph, if you just stare at this graph for a bit, you can see that S seems to only depend on I, right? So which means that the rest of the program can just be deleted. So that's exactly what I'm going to do. So I basically just retain this part of the program, and well, this program is a slice of this program, right? And it can be seen that in order to compute the distribution over S, you just need this program, and the distribution over S for this program is the same as the distribution over S for this program. So which means that if I feed this program to an inference engine, it will do much faster because it doesn't have to deal with extra nonsense, right? But it doesn't always work. So here's another variant of the program where in addition to the earlier program, I also make this observation which is L equals true. So then I do the same thing. I construct the dependence graph which looks like this, and then again I see that, oh, S depends only on I, and I get this program which is the same as the earlier program. But it turns out that the distribution for this program is not the same as the distribution for this program, right? So this is an incorrect program, and I'll say why in a little bit. Right. So maybe I'll say it right away. So essentially the reason why this happens is the following, and the culprit here is indeed this observed statement, right? Standard slicing techniques don't even understand what an observed statement is. So the fact that you observe the statement, right, basically means that there are dependencies which flow in this direction and this direction. So because L is observed to be equal to true, there's an indirect dependence, implicit dependence on G. G depends on L, and because G depends on L, G also looks like it's observed, and there's a flow of information in this direction, which essentially seems to say that the slice for this program is essentially the whole program, because this is saying that S depends on I, D, G and L, right? So the question is, again, the interesting question is, what would be a correct slicing algorithm for probabilistic programs, again with the purpose of improving the efficiency of inference. So here's another example where standard slicing is inefficient. Again, same program, except that I return L and observe G over here. Again, if you look at this dependence graph, standard slicing would say, well, L depends on this part of the program and not on S, so you get this guy. But it turns out that you can do better. Because L is observed, you get this dependence L to G, and the rest of the program, because G is observed, you get this dependence, and since G is observed to be false, all the rest of the dependencies are sort of eliminated, and essentially what you get is that L depends only on G, which is like this, And then if you do some data flow analysis, I don't know if you heard the word constant propagation, but if you did, then if you do constant propagation, you get the small program. Right? So this program is equivalent to this program. And when I say equivalent, I mean equivalence in the most formal sense with respect to the semantics of the program. Right? So according to the semantics that I defined earlier, this program is the same as this program. Right? So quickly, what is an observed dependence, right? And essentially, again, the point of showing you these slides is not to really tell you the nitty-gritty details of what the algorithms are, but to say that it's quite exciting to work in an interdisciplinary area, because right now what I want to define a well-defined program analysis problem, which is slicing for probabilistic programs. It turns out that well-defined notions of slicing for regular programs, which are deterministic / non-deterministic programs, will not work. So therefore, we're going to sort of also look at what is the notion of dependence in Bayesian networks, right? And again, there is a notion of a dependence called active trail in Bayesian networks. And essentially, since you guys know what a Bayesian network is, I just take this example here. So if I look at this example, I have a Bayesian network which represents this distribution, and if Z is not observed, right, there is no flow between X and Y. But if Z is observed, then you get this flow, right? And this is a pattern which is quite common in Bayesian networks. So we use this and combine this with standard notions of dependence in program analysis to sort of get the algorithm. And since I am out of time, I'll just skip through most of this. Just to say that if you're interested, there's a paper that we wrote up which essentially says that, formally speaking, that if I use the slicing algorithm based on this observed dependence, I get a program called sli of P, and that's semantically equivalent to P. So this is quite different from regular program analysis, where you just want to show that the set of output states of program P is the same as set of output states of the slice program. That's what typical program slicing proofs would show. But here we need to also count the number of states because it's a probability distribution. So the proof gets very tricky. So that's the exciting part. And then it turns out that the slicing transformation, since it's sort of taking a program and compressing it, is not only useful for our tool, which is called R2, in which the slicing transformation is built, but it's also useful for other tools as well. And this table basically this chart essentially shows this exponential speed up in inference time for 3 tools. This is our tool R2, Info.net from MSR Cambridge, and Church from MIT. Right. So to quickly summarize, I hope I've shown you that efficient inference for these probabilistic programs can be done using very well-known techniques from program analysis. So we've not invented any new technique. We're just applying existing techniques which are well-known in the area of programming languages to problems in machine learning. And I've shown you that you can use this data flow analysis. You can also use Dijkstra's weakest preconditions, and you can also use slicing. It's really an upcoming and exciting new area in the intersection of programming languages and PL. So lots of work going on in this space, and there's interest both from the programming language community as well as the machine learning community. And for further details on those papers and also to learn more about the system, you can look at this website. With that, I'll stop. Thank you.
Thank you, sir, for a very interesting talk. So any questions? Did everybody heard the question? Hear the question? Okay.
How is L
This one?
when L is observed on G? How when L is
G is
observed to
observed.
be true? So
G is observed to be true.
the previous case.
The previous one. This one? Yeah.
So how is the flow of information from D to S?
Yeah, so roughly speaking, right, I mean, I won't get into details, but if you sort of think about this from a Bayesian point of view, L depends on G, right? So which means that there's an implicit table here, which basically says that depending on the value of G, you get a probability distribution over L, right? Now if I tell you that L is true, right, it also roughly tells you what G was, right? So that's why there's a flow of influence in this direction.
So how does it affect S? As in G is true, so
okay. So now G is observed, right? So basically, it's now since G is observed, basically that it's like this, right? So G is observed. Let me just say this in a non-probabilistic way, right? So let's say G equals D plus I, right? suppose I tell you what G was, do you agree that I can't, I mean, if I know what this value is, I definitely know what this value is, so, roughly that's how it works. But there's a well-defined theory called D-separation and so on in Bayesian networks, which sort of defines various patterns along which these non-intuitive flows happen. Because in some sense, if you look at the graph, I mean, G blocks the flow of D to Y, but observing it opens it up, and there are various patterns which do this.
I wanted to ask one more thing. What are the techniques which Church and other algorithms use, as in you use program analysis, right?
Yes.
So what are the techniques?
So Church and other algorithms, essentially what they do is they sort of take the program and construct a likelihood function from it and then use standard MCMC techniques. So they don't really exploit the semantics of the program. Right, so,
shown, all of them correspond to directed graphical models, right? Bayesian networks.
Yes.
Yeah, can say similar things be done for undirected graphical models and?
Absolutely.
So is this R2 whatever you're doing? Can it also handle undirected graphical models?
Yeah, you can have undirected models. You can have Bayesian processes. So I have colleagues in Cambridge who are actually who sort of have specialized languages for handling Dirichlet processes and things like that. So parametric models basically. I mean, so it's very possible. Yeah. And the similar framework can be used, but it can be made much more efficient if you actually know the underlying semantics, that it's a non-parametric model. So you can do much better. So naively speaking, you can code it up as a program, no problem. But if you did some more analysis, right, because they have special characteristics, you can be even more efficient.
So, but probabilistic program can actually capture those models?
Oh yeah, it's just like any Bayesian network can capture those non-models as well, right? So Bayesian network with constructs like plates and there's also something known as gates. Do you know what gates are? So factor graph. I mean, so if you look at Bayesian networks, right, if then else statements, it's a little tricky. You can't write them up in Bayesian networks. So there's another construct by John Wynn and Tom Minka. It's called gates, which they added. So with that, you can do these things as well. But the question, the question is, I think you can model all these things using probabilistic programs. But the nagging question is, so for example, I can do something. Suppose you want to do topic classification for documents, LDA, right? You can write up a probabilistic program for that. But the nagging question is, will it do as well? I mean, so here you have a system which sort of takes a probabilistic program and then synthesizes an inference engine for that probabilistic program. The question is, will it do as well as a handwritten LDA implementation? So that's the question, right? So it's performance mostly. Expressiveness, it's fine. And it's very related to, for example, even in programming languages, if the higher your level of abstraction is, you have to give up on performance because it's easier to write these programs. So for example, I could always write a C or C++ implementation of an algorithm which is way faster than a C# or a Java implementation, right? So likewise, there are similar issues.
Any more questions? Okay, so thank you, sir.
Yeah, thank you and all the best. Yeah.
This is just a token of gratitude.
Thank you.
So we disperse for a short break and meet after 10 minutes for the next talk.